So, dear colleagues, good afternoon to all. It's my great pleasure to introduce our esteemed speaker for today's lecture, Dr. Bálint Vető, an associate professor at the Budapest University of Technology and Economics. Dr. Vető earned his PhD in 2011 under the supervision of Bálint Toth, and since then he has made significant contributions to the field of probability theory. Following these doctoral studies, Dr. Vető held a postdoctoral position at the Hausdorff Center for Mathematics at the University of Bonn, where he worked with Patrick Ferrari from 2011 to 2013. He later served as a postdoctoral fellow of the Hungarian Academy of Science between 2013 and 2016. Dr. Vető research focuses on asymptotic fluctuations of models within the KPZ universality class, encompassing fascinating areas such as interacting particle system, non-interacting trajectories, directed polymers, and random dealings. Additionally, he has contributed to the study of stochastic process with self-interactions. Today, Dr. Vető will present his work titled Moments of the Superdiffusive Elephant Random Walk with General Step Distribution. We are honored to have him with us and look forward to his insights into this intriguing topic. Please join me in welcoming Dr. Bálint Vető. Please, you can start, Doctor.
Thank you very much. First of all, let me say thank you for having me, for the invitation to this seminar. It's my great pleasure to give this presentation on a work on the elephant random walk with general step distribution. Please, anytime interrupt me if you don't hear me, don't see something, if you have any problem. I mean, if you have a mathematical question, I'm happy to answer. So first of all, I would give you an overview what this talk is built up. In the first part, this is a bit longer introduction. I will tell you what the elephant random walk is. I will talk about the phase transition and the asymptotic results, how after many steps the displacement in the elephant random walk looks like, and a little bit about the history. So that's the original elephant random walk model. And our contribution is when we introduce a general step distribution. This is the second part. I will tell you what the model is, how do we generalize the original one, and I state the results. And since these results are, I hope, easy to understand, I plan to have spend some time on explaining the ideas about two parts of the theorem, about the limiting moments and about the LP convergence. So that's how this talk is going to be built up. First of all, before starting with the definition, let me mention that it is a joint work with József Kiss, and this paper is available in the Electronic Communications in Probability from 2 years ago. So what is the elephant random walk? The elephant random walk is a stochastic process, a discrete time stochastic process on Z, on the integer lattice, which has a memory. It is nearest neighbor, so it jumps up or down by 1 in every step, and there are two parameters, P and Q, which are probabilities, so they are between 0 and 1. The first step, so first of all, I will define what are these steps, what are the increments of this walk. The first one is special. The first step is chosen according to the distribution that x1 is equal to 1 with probability q, so that's the probability that we go up, and with probability 1 minus q we go down by 1. And what happens after, it depends on the parameter, it relies on the parameter P, and it is chosen so that in every step, independently in all the steps, assume that the steps from 1 to n have already been sampled. Then I select a uniform index, which I denote by capital K. This is a random variable uniformly distributed on the set 1 to n. And with probability P, after having this random index, with probability P, I repeat the step at time K, or I take the negative, so the opposite of the step at K, with probability 1 minus K. And I do it in every step independently from everything else from the past. I mean, the sampling of this index is independent and it does not depend on the past. Then what we consider and what we are interested in is the sum of these steps up to n. So Sn is the sum of the x's from 1 to n, the displacement, and the questions. What we would like to understand is the asymptotic behavior of Sn as n is big, as n goes to infinity. What is the leading order? What are the fluctuations? And questions like these. Okay, so this is the classical elephant random walk. Let me mention that it is closely related to the Poya type urns, which is a more classical probabilistic model. We have an urn. The Poya urn is the following. Actually, this type of Poya urn that is related to the elephant random walk. It consists of it is an urn with two colors of balls, rose and lemon. I chose these because these two colors, because when Rn denotes the rose balls, number of rose balls, Ln denotes the number of lemon balls after time n, and then they will correspond to the steps to the right and steps to the left. Okay, so that's why these two funny colors came up. And we initialize the urn already in a random fashion, so that we put a single ball at the beginning to the urn, but the color is random. It is Q with probability, it is rose with probability Q, and it is lemon with probability 1 minus Q. Okay, and after that, what happens is that we select one ball in every step. We select a ball from the urns, from the balls in the urn uniformly at random, and we return this ball into. We replace the ball chosen to the urn, and we add an extra ball, and the color of the extra ball is the same as the one that we have sampled with probability P, and with probability 1 minus P, we choose the extra ball to have the opposite color, okay, the other color. So that's the dynamics. It is somewhat similar to the classical Poya urn, and why it is interesting is because the process Rn minus Ln in this urn model has the same distribution as the elephant random walk Xn, because Rn corresponds to, so every time when we add a rose ball to the urn, it corresponds to going to the right with the elephant random walk. And the lemon ball corresponds to going to the left. Is there any question?
I think no, but I have a remark. I mean that you mean that Rn minus Ln has the same distribution as Sn.
Oh yeah, sorry, yeah, sure. That's a typo. Yes, not Xn but Sn. Very good, thank you. Of Sn, and this is on the process level, so for every n simultaneously. Okay, so let me talk a little bit about the role of the parameters. So the first parameter Q, which just determines the first step, is what I call initial bias. And there is the other parameter P, which is the memory parameter. It tells us with which probability I repeat the previous one of the previous steps, or I take the opposite. And this lemma tells us, which is actually easy to prove, that if I'm just changing the initial bias, the parameter Q, that only determines the very first step, then the process with general Q can be very easily described by the process with this Q set to be equal to 1. Namely, what you have to do is that you just take a random variable chi Q, which is independent of the process, and this chi Q is 1 with probability Q and -1 with probability 1 minus Q. And if I multiply the process with initial bias equal to 1, I can recover the distribution of the process for general Q. That's why we can say that the role of this initial bias parameter Q is not so important. It is just a marginal parameter. And in what follows, we will assume that Q is equal to 1/2. That's a convenient choice for us. Okay. And let me give you already at this point an alternative definition of the model. I mean, the model with Q equals 1/2. And this will be very useful for the later part when I would like to introduce the general step distribution, but still I'm stick to the case when the step distribution is up or down with probability 1/2, 1/2. Okay, so how this definition looks like? Well, at the beginning, I already sampled this sequence Xi1, Xi2, and so on as an IID sequence of random variables that are ±1 with probability 1/2. Okay, if I just added up these Xi's, then it would be a simple random walk. But instead, what I do is that I set X1, the first step of the elephant random walk, to be equal to this Xi1. And all further steps I choose so that I again sample a random index capital K, which is uniform over the discrete index set from 1 to n. I assume that the steps from 1 to n are already sampled. And once I have this random index, I choose the step at the time capital K with probability alpha. And with probability 1 minus alpha, I don't take the minus x like in the previous definition, but I take a fresh new copy of the same from the same distribution. So Xi n+1, which is for sure independent from everything else what we have seen before. I mean, with the elephant random walk. And in this way, we can generate Sn to be equal to the sum of these x's. And it is not hard to see that the two definitions that I gave to Sn are equivalent in the sense that the two processes are equal in law. So it's not a cheating, it's not an abuse of notation that I denote both processes by Sn, because they are actually the same in law. So what it is saying is that the elephant random walk, which I originally introduced with the parameter P, and I have to restrict P between 1/2 and 1. For smaller P's, this does not really work, this correspondence, but you will see that actually the P greater than or equal to 1/2 is the more interesting regime. And if I assume that Q is equal to 1/2, then this definition, what I gave at the beginning, is the same as the one that you see on this slide, with alpha, with probability alpha and with this Xi n+1 with probability 1 minus P, 1 minus alpha, sorry. And there is a correspondence between the two memory parameters. So P, I called P as the memory parameter, but actually I will use, so there is the the corresponding parameter alpha, which is just related to P via this very simple linear relation. And actually, I prefer to call this alpha, what you see here, it's better to call this alpha as the memory parameter because this is telling you with which probability, with which probability I have to remember, or the elephant has to remember the trajectory. With probability 1 minus alpha, the elephant can take something which is independent from everything else. Okay, so that alpha is almost the same as the P before. That's just another interpretation. And here is a theorem about the asymptotic behavior of this classical model. Let me go through this. But before that, just heuristically, let me argue that if alpha is very small, very close to 0, or even if you make it equal to 0, then you just get back the simple random walk. And you can believe that if alpha is very small, then this repeating previous steps does not happen very often. So most of the time, you take a new copy from the same distribution. That's why the displacement, the sum of these increments, will going to look like a simple random walk. So that's for small alpha. For big alpha, when alpha is very close to 1, or even if the alpha equals 1 case is of course trivial, then we just repeat the first step and we go linearly. But even if this is not the case, but still alpha is big, close to 1, then it's very likely that a step is going to be repeated many times. Therefore, we expect to have a displacement bigger than just square root of n that we are used to for simple random walk. And that's the case indeed. So if you look at this theorem, you see that there is a phase transition in the value of alpha, and the critical alpha is equal to 1/2. Below that, so in the diffusive regime, you recover what you expect from the simple random walk, namely after scaling by square root of n, we get a normal distribution with mean 0, and the variance actually depends on the exact value of alpha. In the critical case, when alpha is equal to 1/2, then you still have the normal fluctuations, but you have to divide the displacement by something more, not just the square root of n, but square root of n times log n, which is often the case in critical models. And in the super diffusive case, when alpha is strictly bigger than 1/2, then it turns out that Sn over n to the alpha will converge to something that is a non-degenerate random variable, and the law, and one could probably naively guess that Q would be a normal distribution in this case as well, but this is not the case. This is the distribution of Q differs from the normal distribution. The distribution of Q depends on alpha, but it's for no, but it's different, but it's not the normal. Okay, and the convergence here, I mean, in the first two cases, there is convergence in distribution, and in the last case, we have almost sure convergence and also convergence in LP for any P. Okay. Before going into the introducing our results, I will still talk a little bit about how to tackle this problem, or actually I will give on the next two slides, give a heuristic argument why this phase transition happens, what it relies on, and not give a proof of it, but almost. So an argument which can be made rigorous. And it's maybe not very surprising that I will talk next about the martingales, because this model is pretty much related to the Poya urn, and in the Poya urn, there is a martingale which very naturally arises. So here in this problem also we have a martingale. Let's see what it is. Let Fn denote the natural filtration. So this is the sigma algebra generated by the steps from time 1 to n. And with this definition, we compute the conditional expectation of the n plus first step given this sigma algebra up to time n. Okay, remember, now I'm using the second definition. So I said that with probability alpha, I select a random index from 1 to n. So each of the indices, 1, 2 till n, they are selected with probability alpha over n. So with probability alpha over n, I will take x1. So I will repeat that step with probability alpha over n. And this is true for x1, x2, and so on till xn. And with the complementary probability, so with probability 1 minus alpha, I will select a fresh copy of the psi, but it is just a plus minus 1 with probability 1/2. So the expectation of that is 0, and it is independent of Fn. So this you don't see here. So the sum of these is equal to alpha over n times Sn. That's important. Therefore, this is the new step. Therefore, if you compute the conditional expectation of Sn plus 1, Sn plus 1 is equal to Sn plus the new step, and we just computed the conditional expectation of the new step, so you will have 1 times Sn, which is the previous steps, plus alpha over n Sn, the conditional expectation of the new step. But if you look at this definition, this result, then you see that the conditional expectation of Sn plus 1 is equal to just a deterministic factor times Sn. So it's almost a martingale up to this factor. So we can define a sequence An, which is going to be a deterministic sequence An, with which if I multiply Sn, then I get a martingale. And of course, this An should be 1 over 1 plus alpha over n. Okay, so this factor inverted and the product of those, and there is some normalization. So that's the definition of An. Okay, such a product can be written as a ratio of gamma functions. And from the asymptotics of the gamma function, we can read off that this behaves like n to the minus alpha as n goes to infinity. This is just a very simple computation, okay? So that's how we define the martingale Qn. And once we have defined this martingale, it's reasonable to compute its quadratic variation, because this is what determines the asymptotic behavior of the martingale. Okay, so as I said, Qn is An times Sn, where this An looks like n to the minus alpha. And this martingale Qn can be written as the sum of ak times epsilon k. This is going to be a very useful interpretation of the martingale. So this epsilon n, we can compute what it is. What I have to do to compute epsilon n, to take the difference of Qn plus 1 minus Qn and divide by An. And if you do that, just if you plug in the definition, Qn over An is nothing else but Sn, and Qn minus 1 over An is almost Sn minus 1. There is just a ratio of these alphas, but this ratio of these A's, but these A's are products, so it will simplify, and you will recover something, really the conditional expectation of Sn given Fn minus 1, which can be written like the nth step minus the conditional expectation of the nth step given the sigma algebra at n minus 1. Okay, and if this step is just a plus or minus 1, this is a bounded random variable. So we can compute this predictable quadratic variation at time n, just simply using this characterization, this representation. Computing this quadratic variation means that we sum this coefficient ak squared, okay? Because the quadratic variation of xn minus this conditional expectation will actually be close to 1. So what matters for the behavior is the sum of ak squared. And how does ak behave as k is large? Well, ak looks like k to the minus alpha. Look here up above. So the square is k to the minus 2 alpha. So you see that this sum is going to be summable or finite. I mean, if you let n to infinity, if and only if alpha is bigger than 1/2. So when alpha is smaller than 1/2, then this sum diverges. And how does this diverge? Well, if you let n go to infinity, then it behaves like n to the 1 minus 2 alpha, if alpha is strictly smaller than 1/2. So the quadratic variation diverges as n goes to infinity, and we can apply the martingale central limit theorem. It is saying that the martingale divided by the square root of the quadratic variation, which in this problem is actually equal to Sn over square root of n, this will converge to the normal distribution. The very same story is true in the critical case when alpha is 1/2, except for Qn growing like the logarithm of n. So we have to divide Sn over the square root of n times log n to get normal distribution in the limit. But in the super diffusive regime, this quadratic variation remains bounded. So even if you let n go to infinity, this is a finite value. Therefore, Qn as it is, which is nothing else but Sn divided by an, just by the definition, and an is like n to the alpha. Sn times an, which is like Sn over n to the alpha, then this will converge. And this is just the last part, nothing else but the last part of the theorem that I have stated. Okay, so in conclusion, the behavior of the quadratic variation will matter, and it will determine the convergence or the scaling of this martingale under which there is a convergence. Okay. Yeah, well, so let me tell you something about the history of this problem. As far as I know, it started in the early 90s when Dresner and Farnum introduced the correlated Bernoulli process, where there was a memory parameter involved. And the model was actually the same as the elephant random walk, but they didn't use this word or this expression for the process. And later in 2004, Heide realized that there is a phase transition in this model in the correlated Bernoulli process. He already conjectured that the limit is not a Gaussian random variable in the super diffusive case, and this description, the introduction of those martingales that I was talking about already goes back to his work. The elephant random walk as it is, and as I introduced, was named and introduced by Schütz and Trimper in 2004. The connection to Poya-type urns was actually explored and exploited by the work of Bauer and Bertoine in 2016. And the work of Berku from 2017 was the paper when the non-Gaussian limit in the super-diffusive regime was proved. Actually, this paper was our primary motivation. So this was which we wanted to generalize when we started working with József. And the way Berku showed that the super diffusive limit is not Gaussian was that he was able to compute the moments, the limiting moments of the displacement. And other almost sure results were derived in the paper. Actually, this heuristic argument for the proof of the phase transition was written so clearly in his work. The elephant random walk with other step distribution was already present in the work of Bussinger from 2018. This was called the shark random swim when the step distribution was heavy-tailed. Bertoan proved or worked on the zeros of the elephant random walk in 2022, where by zeros I mean the return times to zero, how often this happens and what are these distributions. Then in our work we managed to compute the limiting super diffusive moments in the case of general step distribution, which I will present very soon. And let me tell you that there are further improvements since then. The paper of Guerin and Lolin and Rachel from last year is very interesting, and they derive a fixed point equation for the limiting distribution of the super diffusive case. And as far as I know, Lucille Lolin also gave a talk at this seminar earlier. So it's a very interesting work. So let me tell you what models we were considering. Actually, we can just very simply repeat the definition that I gave. I mean, the second definition that I gave for the elephant random walk. Namely, I take an IID sequence, Xi1, Xi2, and so on, for which I don't assume anything about the distribution. I just assume that they have the same distribution, no symmetry, no boundedness, nothing. In the special case, of course, it's a ±1, but it's not required. Okay, and the same definition makes sense. Just I sample a uniform random index from the discrete set 1, 2 till n. And with probability alpha in every step, I repeat the index, the step done at time k, capital K, and with probability 1 minus alpha, I select a fresh copy from this from this distribution, and Sn is the sum of the steps. As I said, there is nothing assumed a priori about the distribution of the steps, so it's surprisingly general, but still to have some results, we will require finiteness of some of the moments. So little mk will denote the kth moment, and capital Mk the centered moments of the step distributions. But the finiteness of some of the moments will be just a very mild assumption. And I give a remark already here that actually in the elephant random walk, also in the general case, every step has the same distribution. What is the non-triviality of the problem is the coupling of the steps, but still it is true that in particular the moments or the centered moments of every step is the same, or the sequence of steps. And we arrive to the statement of our main result. I put it into one single theorem. We are dealing with the super diffusive regime, that is alpha is bigger than 1/2. For the first part, we assume just the finiteness of the second moment of the step distribution. Then Sn, and we have to normalize so that we subtract n times the mean, and divide by n to the alpha. Then it will converge to a random variable capital Q as n goes to infinity, which is non-degenerate, and it is different from the normal distribution. This convergence happens almost surely, but it also holds actually in LP for every P. For LP, you need, of course, the pth moment to be finite. And for technical reasons, we assume that, so the statement looks like this, that if for an even integer P, MP is finite, so the pth moment of the step distribution is finite, then the convergence here above holds also in LP. Furthermore, we were able to compute the first 4 moments of the limiting distribution, provided that the force moment of the step distribution is finite. That here are the formulas which are not very interesting for now. What I just want to point out is that these moments depend on the moments of the step distributions and alpha.
Excuse me, may I intervene, please?
Yeah, sure, please.
Okay, suppose one holds with 0.6.
Okay.
I'm a little bit confused by the statement. If it holds for alpha equals 0.6, then above this value, let's say for alpha equals 0.7, you will have a convergence in distribution to 0, right? Then how do you select your alpha?
Alpha is arbitrary here.
Do you mean that one happens for each alpha between 1 half and 1?
Yeah, it's true for for every alpha it's different, but then it's a different. I mean, for different alphas the processes are different, so it's not a contradiction to hold this simultaneously.
But as I told you, imagine one happens with alpha equals 0.6.
Okay.
Then for if now you choose alpha equals 0.7, the limit in 1 will be 0.
Q depends on alpha.
Q depends on alpha. But this Sn depends on alpha. It's very much dependent on alpha.
Okay.
Yes. Sorry.
Depends on the pattern before.
Because
something anyway with alpha. Okay,
let me go back just a little bit.
Okay. Now I understood. Sorry. Okay.
Yeah. So much more often you will repeat some previous step if your alpha is higher.
No. I forgot that your pattern depends on alpha.
Sorry. Yeah. Sorry. So maybe, but I didn't want to put so much notation. It's already. Okay.
Thank you.
Thank you for your question. So that's the result, and the rest of the talk is about giving you proof ideas about the limiting moments and about the LP convergence. I would like to talk something about the LP convergence because, as far as I understood, it is not written so. It's simple, but still, surprisingly, I haven't found it written down in the literature, even for the simple elephant random walk. I mean, the original elephant random walk. So that's why I would talk a little bit about this. And also, let me say that this phase transition at alpha equals 1/2, I forgot to say, is the same as, so in terms of the P, this critical point is P equals 3/4. I just wanted to mention this. Okay, but if there is no further question, I will proceed to the proof of the limiting moment. So how to compute the moments, the limiting moments, the moments of this random variable capital Q. Okay, so the idea is to compute. First, I'll turn to the second moment. For simplicity, so how to compute the second moment of Q? Q comes from the limit of Sn, so we will derive a recursion for the second moment of Sn. And for this proof, we assume that M1, so the step distribution has 0 mean, so M1 is equal to 0 for simplicity. We compute the conditional expectation of Sn plus 1 squared by writing it as n plus Sn plus xn plus 1, and we square it. We expand the square very simply. And we compute the conditional expectation. The first term is okay, the second is okay. I mean, in the second term, you take out Sn, which is measurable with respect to Fn, and the conditional expectation of xn plus 1 given Fn was already computed some slides ago. And this is still true in the general case that it is alpha over n times Sn. And more interestingly, we compute the conditional expectation of xn plus 1 squared given Fn. Actually, this would not be needed if you are just interested in the recursion on the expectation of Sn squared, but it will be later used. So let me explain how this comes out. And so you are observing the conditional expectation of xn plus 1 squared, and xn plus 1 is with probability alpha over n is equal to x1 squared or x2 squared, depending on which of the previous steps is repeated. This is true for k equals 1, 2, and so on till n. And with the complementary probability 1 minus alpha, you will sample a fresh copy of the step distribution. So it is going to be xi n plus 1 squared. And since it is independent of Fn, it is just the expectation of this xi n plus 1 squared. Therefore, we can write this recursion for the square of the displacement. So it looks like a constant. So the expectation of Sn plus 1 squared is a constant times the expectation of Sn squared plus m2, which is the centered second moment of the step distribution. And this recursion can be explicitly solved and can be seen that the formula, what I stated here, is true. Let me tell you what is the difficulty if you go to higher moments. You apply the same trick, you just expand the cube, for example, and the most interesting term here is this one, is the third one. So the Sn times xn plus 1 squared, from which, of course, you can take out Sn and compute the conditional expectation of xn plus 1 squared, which we just computed in the previous slide. So I just repeat in this big parenthesis the same expression as you have seen before. And you can denote this like Tn to be the sum of the squares of x k's normalized by their second moment. And this expression, what is in the big parenthesis, can be very easily written in terms of this capital Tn. So what you will get is that the conditional expectation of this third term, this Tn comes in. So actually, it is not just a recursion for the third moments of Sn. In the recursion on the third moment of Sn, there is some other term which comes in, and a similar recursion can be written for this mixed moment expectation of Sn times Tn, which is also doable, but I'm just showing that from the third moment on, you not just have one recursion, but a couple of recursions that you have to keep track. And for the fourth moment, not very surprisingly, there are other terms that comes in particular, the cubes of the xk's that you have to sum up. Okay, so that's about the moment computation. And in principle, you could go up higher than fourth moment. It was just that the computations were difficult enough to stop at this point. Okay, so I'm asking if I have a few more minutes to talk about the convergence in LP. This is just 2 slides and maybe 3 or 4 minutes, if it's okay for you. I accept it as a yes. So
yes, it's okay.
Okay, thanks. So we would like to see that the convergence which I showed in the theorem, I'm just going back here. So Sn, M1 is again 0. So Sn over all n to the alpha converges to Q. So what we would like to prove is that this convergence not only happens almost surely, but also in LP. So for convergence in LP, and this Sn over alpha n is the martingale actually that we have in this problem. So this martingale Qn converges to a limit Q in LP if and only if this martingale is actually LP bounded. So we want to show that the LP norm of this martingale is bounded. And we can show this by a recursion on the pth moment of Q. So in some sense, it is similar to the recursion for the moments. We can write this Qn plus 1. We had this very, very nice representation of the martingale that I have already shown, which survives for the general step distribution, that Qn plus 1 is equal to Qn plus this An plus 1 times epsilon n plus 1, where epsilon n plus 1 is the n plus first step minus its conditional expectation, and this An plus 1 prefactor is this ratio of gamma functions for which the asymptotics is well known. So we would like to have, as I said, a recursion for the pth moment of Qn. So we compute first the conditional expectation of Qn plus 1 to the power p. And if I do so, I use this representation. So it's Qn plus something raised to the power p, which I can expand by the binomial theorem. And the k equals 0 term here is just simply Qn to the p. And in the k equals 1 term, there is just a 0, because here when k equals 1, it is just the conditional expectation of epsilon n plus 1 given fn, which is, if you just look at how it is defined, it is completely clear that this conditional expectation is 0. So this term drops out. And for the remaining terms, for k equals 2 or higher, I don't tell you all the details, but you can use the Hölder. So it is a product of two random variables, and we can use the Hölder's inequality to upper bound the expectation of their sum by the pth moment of epsilon n plus 1 and the pth moment of Qn. Okay, to some powers. These exponents are smaller than or equal than 1, and p is an even integer. Therefore, you can give an upper bound. So you can forget about absolute values. That's why it's important that p is an even integer. And what is important is that for the pth moment of Qn plus 1, you can give an upper bound, as you see here. And let me go to the next slide, how we can deal with this recursive upper bound. Of course, you don't have to understand all the details here, but what is important is that here on the left-hand side, we bound the pth moment of Qn plus 1 with a factor times the pth moment of Qn. And how does this factor look like? Actually, here is a 1. And what I'm saying is that this factor in the parentheses is actually quite close to 1, because here is an An plus 1 squared, and An plus 1 squared, it's here, looks like n to the minus alpha, and it is squared, times a constant. This is just a constant, this 2 to the p times 1 plus this expectation. And there is another constant, which constant is again small because it is multiplied by An plus 1 squared. Okay. And we have a lemma that given such a recursive upper bound for a sequence of real numbers, like Bn plus 1 is upper bounded by 1 plus a constant over n to the beta Bn plus some additive small thing. And what is very, very important is that this beta should be bigger than 1, namely the sum of these, of this C over n to the beta is summable, in this case, the full sequence will remain bounded. And this is what we can exploit, because in our case, this an plus 1 squared looks like n to the minus 2 alpha, and n to the minus 2 alpha is summable exactly in the super diffusive regime, that is when alpha is bigger than 1/2. So exactly in the super diffusive regime, this sequence will remain bounded, so the martingale is LP bounded. Therefore, the martingale, which is nothing else but Sn over n to the alpha, this will converge in LP. And that's all what I wanted to say. So thank you very much for your attention.
Thank you. Thank you for this nice talk, Dr. Bálint. Are there some questions, please? Yes.
Could you please go to page 9?
9, sure. Yes, here, the quadratic variation. Yeah.
Okay. In the super diffusive regime,
Yes.
The quadratic covariance here is finite, right?
Yeah. Yes.
Okay. The last line was a little bit hidden.
Oh, I'm sorry. Yeah, so there is a difference in the scaling, which I may have not emphasized so much, that if you think about in terms of the martingale, then the martingale converges in the diffusive and in the critical regime only after normalizing by the square root of the quadratic variation.
Okay.
But if the quadratic variation is finite, then the martingale itself is convergent. But we are not primarily interested in the martingale, but in the displacement of the elephant random walk. That's why we'll rewrite everything in terms of Sn. And this gives us the behavior, the asymptotic behavior of Sn, and we find that Sn divided by square root of n is in the diffusive regime, and Sn over n to the alpha, what is the corresponding quantity.
Perfect. And do you have an idea on the class of this limiting class of distribution in this case?
You mean what kind of distribution we can expect?
Yeah, something stable, no?
I don't know. That's a very good question, actually, and it's open. Let me tell you, or let me refer you to this last paper from 2023. They went much beyond than us, in the sense that they could not only determine some moments of the limiting distribution, but they were able to write down a fixed point equation for this distribution. They could, as far as I know, they couldn't really write down like density or something like this, but they could show that it is absolutely continuous and some very nice properties about the distribution. But of course, this is only true for the original elephant random walk. So for us, we were trying to give something more robust, like that our step distribution is pretty much general. If the step distribution is plus or minus 1, then this fixed point equation and this pretty good understanding of the limit is valid. I mean, it was explored in this paper.
Okay, thank you so much.
I think that the reference of the paper of Biesinger 2018 deals with this phenomena, the stability and stability of the process of the limiting distribution. I'm not sure, but I think.
At the moment, I'm not pretty sure what is the result there, but what this heavy-tailed step means is that they choose the step distribution, so similarly to our work, to be a heavy-tailed step, and I'm not sure, and I think it's so if you come to our result, we assume that the second moment of the step distribution is finite. To say anything, it is required, and in that case, of course, for stable random variable, it's not the case. So it does not fit into this regime that I was talking about. And as far as I remember, also their critical point is somewhere else, and it will so it's something like 1 over alpha, or I'm not sure, or 1 over beta. I'm sorry, 1 over beta, where beta is the parameter of the stable, or something like this is the result in this paper of Pusinger. But I'm not sure about whether there is anything about the distribution of the limiting random variable, which is of course the most interesting object to study here.
Other questions, please?
Yes, I have a question.
Yes, Mohammed.
Yes, thank you very much, Professor Vető, for this nice talk. I have a question about, I didn't remember if you spoke about this, the asymptotic normality, the central limit theorem question on your model. Did you think about this question? And okay. I did not understand if this result on page 7 is the result on your model, or it is a result about the elephant random walk model by Schütze and Trimper.
As I stated here, this is true only for I mean, in the talk was built up that at this point only the original elephant random walk was defined, so this refers to the original model, and I think that for us it's not very hard to show normality, and in the same diffusive behavior can be shown, I think. Actually,
yes, except maybe if I understood your model, the step in your random walk, in your elephant random walk model, are no longer bounded. No?
Yeah. That's a good point. Yes. Yeah. Now I sort of remember. So but it's not in our paper. Actually, this proof goes through almost for general step distribution. And here, when I was saying that the martingale central limit theorem can be applied, there also a Lindeberg type condition has to be checked.
Yes.
And exactly what you pointed out is a very good point, that that you have to, or to, for this proof to work nicely and in an easy way, it's natural to assume that the step distribution is bounded, and if the step distribution is bounded, then I think that this Lindeberg condition can be easily checked, like in the original case, and then it goes through. And I'm not sure, and we haven't really put an effort in thinking about
this direction.
Unbounded step distribution and normality, and I can imagine that it fails. I can imagine, yeah.
Okay, thank you.
Yeah, like in the if you just take the sum of heavy-tailed random variables, the sum is not going to be normal. It's similar. It could be similar to that.
Thank you very much.
Yeah, thank you for the question. Very good question.
Other questions, please?
Yes, please. Yes, I have a question.
Yes, Youssef.
First of all, thank you for your presentation. It was very clear and very well explained, so thank you for that. Can you go please to the 9th page?
9th?
My question is about the predictable quadratic variation. I can see that it's less or equal than sum of a square, but I don't see how you manage to prove that it's equivalent to the sum squared of a.
Well, It's because, so why is it not just a one-sided bound?
Yeah.
I think it's somewhere. So this computation comes from this paper of Berku from 2017, and you are right that the one-sided inequality is easy to see, and somehow he managed to write down an expression for the quadratic variation in which so somehow if you compute this the expectation of the square of it, you see that it's a so you have to take the square of xn. So if you compute really the quadratic variation, then you would take the square of this epsilon n and compute its conditional expectation. And it is true that you can compute it like the expectation of xn squared minus the square of the conditional expectation. And what is nice about it is that the square of, so that's one observation, that the square of xn is equal to 1 in this case, because xn is just either a plus or minus 1.
But the other term, the problem is with the other term, because we have
The other term, yeah.
like the expectation.
The expectation of
I think there is no problem when the steps are bounded in the original model. It's not difficult to control the conditional expectation of the square of epsilon n, but what is important is when the step is not bounded. But if I understood what you told us, Professor Vető, in slide 9, it is still the model with the bounded steps. No?
Yeah. Yeah.
That's the reason why the quadratic variation is equivalent to the sum of the square of AK.
Yeah.
I think.
Yeah, I was just trying to come up with an argument that it is not just an upper bound by AK squared, but also lower bounded by like maybe 1 minus epsilon times sum of AK squared. But I cannot really give you a precise argument at this point. Just I'm sorry.
Maybe I think it's due to the fact that because the expectation of epsilon square, it's 1 minus one quantity, and this quantity maybe it goes to 0. That's why.
That's true. Yes, it is true, but but I don't really. Okay, yeah, it's something like this. But so it's not. It's just somehow that you compute and you find this. So this is the first guess what you would make, that that this quadratic variation is like the sum of the AK squared, and it turns out that it is true, but you have to work a little bit for that, yes, and to show exactly what you said.
Yes. Thank you.
Thank you.
Other questions? I think Outstar Swissy has a question. Yes.
Thank you for this nice talk. So could you please go back to the slide when you stated the 3 phases? I mean,
when I said the 3 regimes, this one?
Here, okay, good. Here we can see that in the first case, the diffusive regime, we have the family of limiting distribution are all normal distribution.
Yes.
Are there informations about the super diffusive case where Q is indeed Q alpha? Are they the same distribution with different parameter, or we don't have such information?
So could you repeat, please, that if
I mean the limiting distribution in the third case is Q of alpha, depending on the parameter.
Yeah,
is it the same case as the first one? For example, it's a family of random variables with the same distribution. For example, Poisson of lambda, or are they the same nature or not?
You mean about the distribution of Q? That's what you are asking?
Yes.
Well, we don't know. We don't know.
Okay.
So that's an open question. That's a big open question, and that's why actually I got interested in this problem. Is that okay? Here is a very simple model like the elephant random walk. Even in the original case, no general step distribution. You can prove normality in the below alpha equals 1/2, and above 1/2 you don't have any information, or basically almost no information about the limiting process, which seems a bit disappointing, right?
I see.
How
Because
hard it
indeed,
is compared to using just standard techniques like Martingale central limit theorem in the diffusive case.
yeah, indeed, some additional phases may appear depending on the distribution of Q. Because here you said three phases.
Yeah,
depending, because you don't have
yes.
enough information, but depending on the limiting, some other phases may appear.
Well, if you call another phase, if the limiting distribution belongs to other families, then maybe yes. I don't know. Yeah.
Okay, thank you.
Yeah, so it's really an open problem. So it's on the field. If you can give more information about the limiting distribution, that's a great achievement. Yeah.
Yeah, thank you.
Okay, thank you very much for
And
the question.
what about the fluctuation in the super diffusive regime? What about
the fluctuations?
Yes, about the distribution of the fluctuations. Sn over n power alpha minus q.
Yeah. I think there are papers like this, but we haven't looked at that. I mean, for the original elephant random walk, you can indeed do what you suggest to subtract q, and
Yes.
then I think that there is normal fluctuation on some scale, which I don't remember.
Okay. Please, if you can go to slide 1 or 2, maybe. Slide 1 or 2. No, after, please. Go on. Okay. Where we present your model, alpha and yes. Okay. No, sorry.
This
okay.
One,
yes. So when alpha equals 0, we have the classical random walk. Okay.
Yeah, exactly.
And psi n are IID. So if alpha is not equal to 0, are there some dependence between the steps xk? Or my question is, can I confirm that the covariance of xk plus n when n goes to infinity goes to 0? There are some independence. The dependence between the steps becomes weakly when the distance between the past and the future becomes very large.
Yeah, I think so, because the fact from which the dependence comes from is that some step gets repeated, right?
Okay.
Otherwise, they are independent. And I guess so. If you shift yourself later in time, then okay. Wait a second, but I'm not sure, because okay. So what happened? So there are other methods in the literature, like you can actually build a tree, I think, parallelly to sampling the elephant random walk, and it looks like so somehow you or I don't know why is it a tree. So it's like you can create a partition of the index set that you have already seen before, namely which are those indices which are equal with probability 1. It's more clear in the general step distribution case that where all the values are of the size are different. Okay. So you can make a part. So let me state it a little bit more clear that suppose that the realization of your size are different, all different. Okay. Which you can make sure if the step distribution is continuous. And you can create a partition of your steps so that you declare two steps to be equivalent if their value is equal to each other. Their values are equal to each other. It does not mean that in the later step you have repeated exactly the one that is the other step, but it can happen also that they are repetitions of some previous steps. Okay? So in this way, you create a partition. And with this method, you can actually. So what was your question? So your question was for what is the decay of the correlation between?
Yes.
So what I'm trying to say with this is only that if you shift yourself later, then the correlation may not decay because there are more, as time goes by, there are more and more equivalent copies of the same step. Okay.
Maybe it will depend on the value of alpha.
I can very much imagine that. Sure.
Maybe it's possible to get some mixing condition or something like this, depending on the value of alpha.
So and my feeling would be, if combining with the suggestion that you said, is that probably it's related to the phase transition that I'm showing, because this mixing is often related or used to prove normality. So I could very much imagine that there is so in the diffusive regime there is a decay of correlation, and probably in the super diffusive regime there is another kind of behavior of the correlation, or something like this sort. But I have never tried to compute that, but that's maybe an interesting question. Sure.
Okay, we may discuss this problem later by email.
Possible.
Okay. Another questions, as in the work of Bertrand 2016, are there some connection with polyairons for your model? Is your model can be connected to some kind of polyairons?
Sure. But the problem is that the corresponding polyairn in our model would have more colors. So that's the difficulty.
Okay, because you use in UXI sometimes.
So let me go back to this connection to the EARN model. Here, the rose balls that are the right steps are corresponding to the +1 steps, and the left lemon balls, the left, correspond to the steps equal to -1. And if you introduce a more general distribution, then every possible step size would have its own color, right? And if you have a continuous distribution, then every time you have a different color, which makes it quite difficult. Already the case of maybe a distribution with concentrated on 3 points is already non-trivial general step distribution, and in that case you have 3 colors in the polyairn. That's probably something that you can handle.
Okay, thank you. We have a lot of questions, but we can discuss this later, as I told before. Are there some other questions, please? If not, we have to thank again Dr. Bálint Vető for this nice talk and nice topic. Please, can you send me the slides for our website, please?
Yeah,